Welcome to part 12 of Zombies and Reinforcement Learning. In this video, we're going to go ahead and start coding out the agent. So let's get right to it. All right, so we've already created an agent, agent.py. We're actually going to delete this line that we created in the last video because it is not necessary. And we're going to go ahead and do some more of our imports. So we're going to say from buffer, import replay buffer. This is really the class where it all kind of comes together. We're going to import torch, not token, torch. We're going to import torch.optim as optim. We are going to import torch.n.functional as f. We will import date time. We will import time. From torch.utils.tensorboard, import summary writer. We're going to be using tensorboard to manage our logging. We'll need random. We will need OS. Okay. So our class name here is going to be agent. So just go down a couple lines and then do class agent. Okay. And then we're going to say def init. And we won't just need self here, we will also need env, dropout, hidden layer, learning rate, step repeat. That's going to be how many times in our environment it runs a given action, and gamma. All right. So in here, we're going to need to go ahead and say self.env equals env. We'll assume that we're passing in an environment. Self.step repeat equals step repeat. Self.gamma equals gamma. We will go ahead and get an observation and info. So observation info from self.env.reset. And then we'll go ahead and see if we have CUDA available. So self.device is equal to CUDA 0 if torch.CUDA.is available, else CPU. And this is basically just checking to see, do you have a GPU, loaded? And then we're going to just give ourselves some output here. Model loaded on self.device. Okay. So we want to, and that's really because if this thing starts up on CPU, I don't necessarily want it to crash, but I really want to get some information on that. I want to find out, are we running on CPU? Because it's going to be really, really slow if we are. All right, we're going to say self.memory equals replay buffer. Max size equals 500,000. Now a word on this one. So this is expecting to be able to build a replay buffer of 16 gigs. If you have less than 16 gigs of memory on your computer, or maybe you're just, you have 16 gigs, but you need something to actually run your operating system, you may want to reduce this. Now, 500,000 is what I tested it with. It's what it works with. There's nothing saying you can't get by with a smaller replay buffer. That's something that you need to play with based on your own system memory constraints. So that is what I'm recommending, but if you need to drop that down, if you've only got 8 gigs, make it 250,000. If you've got a little bit more, up it. All right, we're going to do input shape is going to be observation dot shape. We will make n actions equal to env dot action space dot n, and device equals self dot device. And give me just a moment. I want to see if we actually defined an action space in the environment. And I don't think we did, so we need to. So let's come back over here to game. And up here in the init method, we are just going to go ahead and say self.action space is equal to gym dot spaces dot discrete 7, and we may need to import gym up here. So we're going to say import gymnasium as gym. Okay, and now over here, hopefully that will like us a little bit more. Okay, so that successfully defines memory. Now we're going to do self.model1 is equal to zombienet, and action dim equals env.action space, and we can actually tell it what env is so that we get our autocomplete. So if you come up here and put this down as zombienet, now we should start getting, we're still not getting action space. Just save all. And it may just not want to, not be ready to reread it. That's okay. So we'll go ahead and say action space dot n, hidden dim is going to be equal to hidden layer. Dropout is going to be equal to dropout. Oh, and you know what? There's my mistake. I said env equals zombienet. What I should have done is env equals, see, we don't even have it imported. That's why. From game import, what do we call it? We called it zombie shooter. Not strictly necessary to make the code run, but again, it's going to get us, it'll help it understand what the env is. All right, back down here. So we got as far as dropout. We need to do observation shape equals observation dot shape. And then we're going to take the whole thing and say to self.device. Okay. And then just copy and paste that. And you know what? It really helps if you put an equals there and there. And this is going to become self.model2. All right. All right, so we need to go ahead and create our target models. So really this can just be another copy. There's nothing special about the target models. So we're just gonna paste. And we're just going to relabel these target model 1. And target model 2. And then we can go ahead and say self.targetModel1 Actually, this is where we can use our hard update. And we can say self.targetModel1. And our source is going to be self.model1. And then just copy and paste that. And we will do the same thing for target model 2 and self.model2. Okay, we have successfully created our models and our target models. Now we can go ahead and say self.optimizer1, because each model gets its own optimizer. We're going to say optim.atom and self.model1.parameters. And then we'll say LR, so the learning rate equals learning rate, and self.optimizer2 is equal to optim.atom as well. I could have copied, I suppose. Model2.parameters, and then LR equals learning rate. And we're using 2 here because we're going to take the min value between them, and that's going to help protect us from over allocation. Or sorry, over confidence, not over allocation. Self.learning rate. Let's go ahead and do this. Equals learning rate, just to have it available. And then we're actually going to pull in one more import. This should help you figure out, sizing. So from Pympler, if I'm pronouncing that right, we're going to import a size of. And here, we're actually going to make the model spit out the size of memory, or the agent spit out the size of memory. So we're going to say print f, and we're going to say memory size, and then a size of, and dot a size of self.memory. And then we'll do a little bit of calculation here. So we're going to say divided by, and we could just punch a number in here, but it's easier for me to see it in as the multiples. So 1024. Okay, times 1024. And what we're basically trying to do is break this down into from, I believe the default output is bytes to gigabytes. So that's going to give us the total size of our replay buffer that was just implemented in gigs. So, okay, so when you fire this up, when you create your agent, you're going to get some information on whether it loaded on your GPU, and then you're going to get some information on your memory size. It's worth noting that the memory will load on your standard system memory, your CPU memory. The model itself will load on your GPU. So your GPU does not have to have the same amount of memory as the buffer. You could implement it to where the buffer went straight to GPU memory. I don't recommend it unless you have a really big GPU or a very small buffer. All right, so now we can go ahead and start on our train method now that we made it through init. All right, so we're going to, and there's going to be a bunch of params on this one. So we're going to say def train, and this is going to take self episodes max episode steps summary writer suffix. It's going to take batch size, epsilon, decay, and min epsilon, because we're using an epsilon greedy action selection here. Okay. We'll go ahead and define, so the summary writer is something that we're using with TensorBoard. So that's going to help us print out what's happening as we go. So we're going to say summary writer name is equal to, and we're going to put it in runs. This will put it in the runs directory. That's not required. You can put it anywhere you want. I'm going to say datetime now strftime, and then this will be percent capital Y dash percent lowercase m dash percent d underscore percent h dash percent capital M dash percent capital S. And that should get us year, month, day, hours, minutes, seconds in the file name. And the reason we're doing this is so it doesn't just overwrite every time. It will automatically pick it'll automatically pick a new file name for us just based on the time. All right, and then we're going to say underscore, and we'll put in summary writer prefix or suffix. And the reason we're doing this is we want to go ahead and we want to have a default name, so a time, a number that gets incremented every single time. But we also want the ability for you to label each run. Now maybe, because you're following a video tutorial, you're only going to run this a couple of times. You'll run it, hopefully it'll work, and success. But that's not how these things usually work. So I mentioned at the beginning of the series that I started this back in October as kind of a joke Halloween project. And it took, a couple of months of tweaking to get everything working, specifically on the model and training side. And that meant that every single time I wanted to change parameters, I needed to have a way to label it, to log it, to see which parameters did better, which ones did worse. And that summary writer suffix, that variable, is allowing us to track that, to label our runs a little bit more easily. All right, so we're going to say writer equals summary writer, and we will be passing in summary writer name. And then we'll go ahead and create the path if for the models, os.path.exists models, oh, put it in quotes, then os.makeDirs models. Okay, we're going to set total steps equal to 0. And then we're going to say for episode in range episodes and we will say go ahead and start out with done as false, and episode reward equals 0. State info equals self.env.reset, and that should get our initial state. We'll say episode steps will also start out equal to 0, and then we will go ahead and say we're going to go ahead and capture episode start time equals to time.time. And this is just to monitor speed. This was also really important starting out because initially the game ran really slowly, and that impacted how fast training could run. So we want the ability to see how long things are taking. All right, we will go ahead and say while not done, and episode steps is less than max episode steps. We're going to go ahead and do our epsilon greedy action selection. So we'll say if random.random, not randint, if random.random is less than epsilon, then action will equal self.env.actionspace.sample. Else, we're going to say q values 1. So we're going to call self.model1.forward state.unsqueeze on 0. So we need to do a little bit of reshaping on state because it's not a batch. .2. So we're going to go ahead and send state. Remember, we're pulling state from an environment, and then we need to send it to the model. But the model is running on the GPU. So we need to go ahead and send state to device. And that's going to be self.device. And then we need to grab the 0th element. All right, and then go ahead and copy and paste that. And we're going to do q values 2. We'll call model2.forward. And then we're going to say the actual q values are equal to the torch.min of q values 1 and q values 2. And again, what we're doing there is we're trying to reduce overestimation. We're trying to stop this thing from, accidentally having one model that really thinks an action's good and the other that doesn't think it's all that great. We're going to go with the one that doesn't think it's all that great. We want this to be a little bit more pessimistic about its selections. And then finally, we're going to say action equals torch.argmax, and we're going to say q values and dim lost our paren there. Dim equals -1 dot item. So what this will do, again, our existing output is going to look something like, you know, this, but with probabilities. This is going to convert that, you know, type of distribution into, hey, this is action, you know, 2 or 3 or, you know, whatever the highlighted value is. That's what our torch.argmax is going to do. All right, we're going to go ahead and take a step in the environment. So next state, reward, done, truncated. Actually, we're not even using truncated or info, so let's just do underscores for those. Equals self.env.step. And we're going to feed in action equals action, and repeat equals self.step repeat. Okay, so now we have taken our step in our first step in our environment. We can go ahead and store that transition. So this is where we're putting away the memory for future training use. So we're saying self.memory.store transition, state, action, reward, next state, done. We'll go ahead now that we've stored it, we can say state equals next state. We can go ahead and add episode reward plus equals reward. We can add episode steps plus equals 1. We can do total steps plus equals 1. And then we get down to the batch training section. So we're going to say if self.memory.can sample batch size, then states, actions, rewards, next states, dones equals self.memory.sample buffer of batch size. All right, and then we are going to need to make some changes to those values. So we're going to say dones is equal to dones.unsqueeze on dimension 1 dot float. And then we will get the Q models from both, or Q values from both models. So current Q values. Okay, so we're going to do Q values 1 is equal to self.model 1 states. Very easy to typo something in here, so be careful. Q values 2 is equal to self.model two states. We're going to say actions equals actions dot unsqueeze 1 dot long QSA B 1 is going to be equal to Q values 1 dot gather Oh, it helps if I spell gather correctly. 1 on actions. So what's this line doing? This one is actually taking, so we just got a batch of Q values back from these models, right? So this was a bunch of values of which directions have, or which actions have which values. We're grabbing a long version of actions, and then what this gather is doing is it's taking the actions and it's grabbing the predicted Q values for those actions. So what this QSAB1 is the Q state action, the batch, so the values of the batch of actions. And then just like everything else, we're going to go ahead and turn that into a 2 as well on Q values 2.gather. Okay, so next we're going to go ahead and select a fresh batch of actions. So we're going to say action selection using main models. Okay, so we're going to say next actions 1 is equal to torch.argmax, and we'll say self.model1 next states. And we'll say dim equals 1 and keep dim equals true. Copy and paste that. And next action's 2. And you have to change model to 2 as well. And then we will go ahead and get the Q value of next states using the target models. So we're going to say next Q values 1 is equal to self.targetModel1 next states, and that will be added a dot gather 1 and next actions 1. And just like before, we're going to copy and paste that, and that will also be added to number 2 here, and model 2 and next actions 2. All right, and then we're also going to take the minimum, just like we did in the real action selection. So take the minimum of the next Q values. Okay. So we're going to say next Q values is equal to torch.min next Q values 1 and next Q values 2. Okay. We will compute the target value. And that's going to be target B for target batch equals rewards dot unsqueeze 1. And unsqueeze is just adding an extra dimension, if I haven't mentioned that before. So that's going to be 1 minus done times self.gamma times next Q values. Okay, so let's talk for a moment about what's happening here. So we're looking for the value of the target batch. And we're doing that by saying, so we in the target batch is, your next state, the value of the next thing that you're doing. So the first thing we're taking is the reward. We know what the rewards are. So, maybe the reward is a 2. We know that, or a 1. We know that the current reward is a 1. We are then looking for what the next predicted value is. So that's next Q values. And we're multiplying it by gamma. And gamma is the discount factor. So the discount factor in this case is 0.99. So we're basically saying that future rewards, because they're not necessarily guaranteed, they're just predicted, we're saying future predicted rewards are still very highly valued, but they're valued a little bit less than current rewards. So your current reward is the real reward, whatever you're getting right now. Your future predicted reward is devalued by basically 1% based on what we're passing in. And let's talk about what 1 minus done means. So done is going to be a value of 0. So most of the time, if it's not done, it's 0. So if the episode is still going, if that wasn't the last step, then 1 minus done just turns into 1, and then it doesn't change the value of the equation. You're just multiplying 1 by self.gamma and next Q values. If it is done, so done will come back as a 1, then 1 minus 1 ends up equaling 0. And then it basically cancels out the second half of this equation. So you will, if you're in your terminal state, if you're done, there's nothing else to do in the episode, then there obviously is no next Q value. There's no next value of an action because the episode's over. There's nothing else you can do. So that's what's going on there. So we're going to go ahead and calculate our loss. So loss 1 is equal to f dot smooth L1 loss on QSA B1 and target B, and we'll have to detach that. And we're just going to copy paste that. And we'll do loss 2 will be QSA B2. And then we'll go ahead and do, this is our TensorBoard section. We're going to do writer.add scalar. And this is going to be loss / model _1. And these should track pretty closely, but it is interesting information if they're not. So we do want to track loss for both of our models. So loss1.item. Oh, I did not mean to go there. And then we'll do total steps. And the reason we're doing total steps, and the whole reason we're tracking total steps is actually for TensorBoard, is we want to see a loss trend that covers across episodes. So we want to see loss over the entire course of training, not necessarily loss for a single game, a single play. So we can go ahead and copy and paste that. So we'll do loss model 2, loss2.item. And then I had also wanted to add some comments here. Compute loss. Okay, So we've successfully computed our loss. We've got all our values. Now we need to go ahead and do backprop and optimization. Okay, so we'll do self.model1.0grad loss 1.backward and self.optimizer1.step, not state, step. Okay. And then we're just going to copy and paste this. And I did not copy and paste the way I wanted it to. There we go. All right, we're going to do model 2 and loss 2 and optimizer 2. Okay. So we have successfully done our optimizer step. We've gotten our loss, and then we want to go ahead and do our soft update. So we're only going to do it so often. I'm going to say if episode steps %4 is equal to 0. Then we're going to do a soft update and self.targetModel1 and self.model1. And copy and paste that. And self.targetModel2 to self.model2. All right. Now we're going to come in a couple layers here. So we want to be out of the for loop, but still inside train. So that's going to put us, actually, hang on. We want to be inside for episode in range. We want to be outside of while not done. All right. So this is perfect. This is where we want to be. So we're going to say self.model model1, sorry, dot save the model, file name equals file name, or actually file name in this case, we don't have file name defined as a variable, so it's going to be model/dqn1.pt. Okay, copy and paste that, and we're going to say model2 dqn2. Simple enough. And then we'll do writer.add scalar score. So this is where we're actually going to track our score over time. So we'll do episode reward. And let's see. And episode. And we'll also do writer.add scalar epsilon. And you might wonder, why do we want to track epsilon? It's something that we're decaying at a predictable rate. Well, sometimes you can see some interesting, changes in performance as epsilon decays. And, you might see that that performance is going down as epsilon decays. And you could, think that your model is getting worse. when in reality, it's just that the model is slowly taking over from randomness. And then once epsilon decays all the way down, you'll start to see the actual model improvements. So we do want to track that because it can affect some of the other variables on the graph, and it makes it easier to make sense of the data. All right, so we'll say if epsilon less than min epsilon, we're going to say epsilon times equals epsilon decay. And episode, let's see, episode time is equal to time dot time, not time dot tim, time dot time, minus episode start time. And then we're just going to say, we're going to give ourselves some output here. We're going to say completed episode with score, let's see, episode reward. We'll do a print episode time, and we'll just format that to 1F seconds. And then we will go ahead and print episode steps. All right, and that takes us to the end of our agent class and the end of this video. We're not going to test it in this one. In the next video, we're going to go ahead and put together a train.py, which is going to tie it all together, call agent kickoff training, and then hopefully you can start to see some results of the AI playing the game. So I will see you in the next video.